Okay. Good morning, good afternoon, good evening. My name is Soumitra Das, and I'm delighted to welcome all of you to our webinar, Stratospheric Aerosol to Cool the Planet. Thank you for taking the time to join us, especially during the holiday season. This webinar is part of the series Technology Intervention for Climate Change, where we explore innovative solutions to cool the planet. While decarbonization is essential, we believe it is equally critical to consider climate interventions to ensure a safer and healthier future for our planet. These solutions involve reflecting sunlight back to the space. Today's session focuses on stratospheric aerosol injection, a promising but controversial, cost-effective solution to rapidly cool the Earth. By deflecting more sunlight back into the space, SAI has the potential to slow global temperature rise, refreeze polar ice, and mitigate devastating weather events. It is my pleasure to introduce our esteemed speaker, Dr. Douglas MacMartin, an associate professor in the Sibley School of Mechanical and Aerospace Engineering at Cornell University. His research focuses on sunlight reflection methods, aka solar geoengineering or climate intervention, with the aim of helping to develop the knowledge base necessary to support informed future societal decision in this challenging and controversial field. He has developed briefings to the UN Environment and testimony to the US Congress, and was a member of the US National Academic Panel that made the recommendation on both research and governance in March 2021. He received his PhD in aeronautics and astronautics from MIT in 1992. His previous positions include United Technologies Research Center, 1994 to 2000, and the California Institute of Technology, 2000 and 2015. His research is funded by NSF and by the Cornell Atkinson Center for a Sustainable Future. Please join me in welcoming Dr. MacMartin. Thank you. So all your ears, Doug, you can.
Okay, thank you. Let me share some slides. And I think some of you have heard me talk before, some of you might not have. I might go through a little quickly through a few places and try to leave lots of time for discussion because I think that's where things are particularly interesting. I've personally taken to calling this field sunlight reflection methods just to sort of use plain English. There's of course a proliferation of terms that get thrown about. And I'm really only going to talk about the stratospheric aerosols injection part. And I don't really need to say anything about climate change in this audience, right? We're, of order 1.5 degrees above the pre-industrial, so we're of order where the Paris Agreement said that should be our target. And of course, still heading up. We haven't managed to peak in emissions yet. I think probably most of you could put your own slides together with, calamitous pictures of climate change. I think when 10 or 15 years ago, people talked about climate change as this thing in the future that our kids would have to deal with. And now basically, it's obvious there's impacts here right now. And we're only at 1.5 degrees and who knows where we're going to get to. So, your basic introduction picture that gets shown, we obviously have to cut our emissions. That is not a solution to climate change. People always like to use the word solutions. I like to point out that nothing is a solution to climate change. That simply stops it from getting worse, we hope. Pull CO2 out of the atmosphere, lots of ideas for that. And of course, all of these have big uncertainties on them. If you tell me exactly what the future emissions are going to be, I don't know how much the planet's going to warm. Nobody does. And I don't know what the impacts of that are. Even if you said, we're going to stabilize at 2 degrees, we don't know whether 2 degrees is how bad it is. We certainly don't know what future policy is, and we don't know what future technology is. And so at this point, anybody who says we have 100% confidence that we are on a path to solve climate change does not understand climate change. People can have different guesses. Some people don't think climate change is going to be that bad. Some people think we're going to zero our emissions in 30 years. Some people think we can do massive CDR right around the corner. Regardless of what your beliefs about those probabilities are, none of those are 100%. So this is basically current climate policy in a nutshell. Is basically pray. For the last 10 or 20 years, people have been saying, oh, we need to cut our emissions really aggressively. And the plots wind up just looking like this. They say, oh, well, we'll just have to cut our emissions even more aggressively. This was actually from a paper in 2016 that said, oh, great, we have 3 years to safeguard our climate. Of course, nothing changed. So now we are on a few days away from 2025. If you do not have CDR and you want to stay below 1.5 degrees with 50-50 odds, which is not very good odds, you basically have to just zero emissions pretty much right away. The alternative, of course, we get all of our energy, virtually all of our energy from the sun, radiate an equal amount of energy back to space, or almost equal. In equilibrium, those two arrows are the same, then the planet temperature stays constant. To the extent that those arrows are out of balance, then we get the temperature has to change until they get back into balance. So of course, one can deal with the greenhouse gases in the atmosphere directly, or in principle, one can modify the incoming sunlight. Those affect the climate in different ways. So if you said, we're going to magically pull CO2 out of the atmosphere overnight and pull 1 trillion tons out, we basically know exactly what that would do. If you say we're going to go turn the sun down somehow, reflect sunlight, that does affect, it has a different spatial pattern on the planet, has a different seasonal pattern on the planet, and it's different in terms of where that energy is absorbed in the atmosphere. The solar energy, most of that is absorbed at the surface, whereas when you increase greenhouse gases, that actually is warming the entire atmospheric column. So that's the really quick, let me get back to turn that off. The approach that I mainly work on is the stratospheric aerosol injection. So we know from volcanic analog, if you put lots of sulfate into the stratosphere, it lasts for a year or two, it reflects sunlight, the earth gets colder. There is zero doubt about any of that. Mount Pinatubo put, I think it was about 20 million tons of sulfate into the stratosphere. Because that puts sulfate into the stratosphere, we usually assume sulfate as a default assumption. And the idea would be you go fly airplanes up to the stratosphere, you release sulfur dioxide gas, oxidizes into sulfate aerosols, it lasts for a year or two. The probability that that would cool the planet is 100%. We know how to do it. The real question is, should we do it? And a little bit more in the details of how we do it. There are, of course, other ways that you could reflect sunlight. I'm not going to talk about them, but you can always ask me questions. And I do a little bit of work on marine cloud brightening, but not very much. I would say of the various ways to cool the planet, this is stratospheric aerosols is probably, in my view, and I think fairly widely shared, but not universally shared, the closest in some sense to being able to deploy. Even there, if you said there was a decision today to deploy something, you're looking at least 5 years probably before you could start doing anything. And I don't think we're close to a decision to deploy. Okay, so back to this figure, the usual description of how you use sunlight reflection is sort of this shave the peak. There is, of course, nothing saying that the temperature at the day that you start deploying is the temperature you want to keep things at. In fact, I would say, personally, it seems likely to me that nobody is going to pull the trigger and say, let's go deploy this, unless conditions are already bad, in which case you would probably want to bring temperatures back down a little bit. And then hope the exit strategy in some sense is eventually, hopefully, people figure out how to pull CO2 back out of the atmosphere. But that might be hundreds of years. We don't know. Okay. Important point, the climate state 2 and 3 aren't the same. As I said before, we know it will cool. And I would say, I want to say a few words about some standard misconceptions. When we're looking at climate modeling, we generally compare as points 2 and 3. And the reason we do that is partly because we want to understand physics. And it is also partly because we want to say, well, we've experienced something kind of like this historical climate here. To the extent that the climate you get when you do SAI is similar to that, that gives you some basis for saying, I understand the impacts. And to the extent that this climate is different from that one, that says, maybe I don't understand the impacts well enough. But of course, from a policy perspective, unless you think this is a one-for-one substitute with cutting emissions, from a policy perspective, the risk trade-off is between points 1 and 2. Hugo. I'll accept that. So that's sort of the first, what I would say is a standard misconception that one often deals with. That comparison that's just the comparison here between these 2 points. Like I said, it's useful for understanding physics, but that's presumably not the correct comparison from a policy perspective. And from a policy perspective, we know it would cool the planet. So in some sense, from a policy perspective, you ought to be looking at comparing the risks of deploying to not deploying. The second thing I would point to, and I feel like I am constantly fielding emails from people who look at papers where we cooled the planet by 4 degrees. So burn all the fossil fuels on the planet, make the planet really, really hot, use stratospheric aerosol injection to cool it down a huge amount. We ran some simulations to that effect, and lots of other people have, because scientifically that gives you a big signal to noise. So you can really better understanding of what's going on. Hopefully that's not policy relevant, because if we're really living in a world that's 4 degrees warmer, if that's the alternative, that's so catastrophic that I wouldn't necessarily be that concerned about geoengineering, about stratospheric aerosol injection. But quite often what we wind up with is people, this paper, this is the Geoengineering Large Ensemble Project, that's been cited almost 200 times now by people doing analyses and so forth. And you'll hear people standing up at a meeting and saying, oh, if you deploy geoengineering, it could cut African rainfall by 20% in places. Like, well, yes, with 4 degrees of cooling, but not very, that works out to 2.5% if you're only doing 0.5 degree of cooling. Same sorts of stories, whether it's ozone or acid rain. I've fielded people, talking about, methane oxidation lifetime, and citing papers that were, again, based on this study that cooled the planet by 4 degrees. The contrast to that is, we know that if you could offset 0.5 degree of warming, that's a big deal. And we know that the climate impacts from allowing an extra half a degree of warming are huge. In some sense, one needs to be consistent. And then the third thing I would say is related to that is worrying about what the uncertainties are at scale. So again, that's kind of thinking, oh my gosh, if you were doing 2 degrees of cooling, we don't know what would happen. My answer is, well, first of all, hopefully we're never in a place we need 2 degrees of cooling. But second, that's okay, because it's going to take a really long time before you would ever get to 2 degrees of cooling. And during that time, you can learn. So if you started deploying and you started seeing things that were unexpected that you didn't like, you can always change your strategy. So, I see sentences, this one's taken from IPCC last assessment report. This particular sentence is probably not too bad, but every time you ever read any summary of geoengineering, it will always include words like, there are large uncertainties. My answer to that statement is that that is not a scientific statement. That is an emotional statement that is trying to get an emotional response. And the reason I say that is because nobody ever defines the word large. And if you don't have a quantifiable definition for what large uncertainty means, there's no way that you can back up an assertion one way or the other as to whether those uncertainties are large. So to me, the only meaningful definition of large would be there are some realizations of the uncertainty for which you would choose to deploy, and there's other realizations of the uncertainty that would cause you to choose not to deploy. And if that is true, then I would agree that the uncertainties are large. I think right now the answer is we haven't done enough work to assert or to at least be able to prove to people that the uncertainties are or are not large. My guess would be that if you actually go do that work, you would conclude that the uncertainties are not large. So that sort of gets to a risk framing, right? One has to trade off what are the impacts and risks of climate change against the impacts and risks of SRM, or SAI, I should say. And you can subdivide that into 4 things. Most of the research, I would say, has focused on this thing on the left. If you deployed something in a reasonably responsible way, what are the physical impacts of that? I don't think that we have made a strong case yet that would convince everybody on the planet of it, but I think the research suggests pretty strongly that the physical risks of a well-designed, responsible deployment are probably smaller than the physical risks associated with not deploying. I think that's pretty likely to be the situation that we find ourselves in. In response, people will point out, well, but technologies tend not to get deployed in a beautiful Goldilocks type scenario. The real world is messier. So I think it is in fact appropriate that one also look at the physical effects of a badly managed deployment. So that's something we're working on right now. And by and large, I would say, short of ramping up to significant cooling and then just stopping it abruptly, which would be bad, but maybe not so bad as having never started, I don't know. It's not obvious that this category of risk is huge. More on the societal side, a standard argument against considering this is the moral hazard or mitigation deterrence. This is the idea that I'll say it more bluntly, if rich people don't see enough poor people dying, rich people aren't going to cut their emissions. And you have to make sure that there's lots of death and destruction in order to ensure that rich people do the right thing. That's my take on I actually find this argument a little bit offensive. But the idea basically is you shouldn't deploy this technology because if you deploy this technology or even talk about this technology, people won't cut their emissions. And the reality is there is often some degree of risk offset. If you look at the adoption of seatbelts or airbags and things like that, it is actually true that you don't necessarily get all of the risk benefit that you should, because people will actually drive a little worse with seatbelts. But it's usually a pretty small effect. It's not a one-for-one substitution. And then this one on the right, I would actually say to me, I think is a very, very serious issue, particularly right now. If a country decided right now, we've decided we're going to go deploy some global geoengineering strategy, whether it's stratospheric aerosols or anything else, without broad support across the globe, that is not going to go well. So even if it would actually make sense physically to deploy tomorrow, it does not necessarily make sense politically to do that. And it probably won't make sense to deploy politically until an awful lot more people on the planet are looking at this and agreeing in some sense that these risks are better than the risks of climate change. And the situation right now is that that's not true. Okay, so just a couple of quick slides on the technical stuff. These are simulations just to convince you that the risks of this are not obviously bad. These are simulations done a few years ago in NSF's big climate model, WACM. The top row shows a map of temperature and precipitation changes under fairly realistic or reasonable guess as to future warming over the next coming decades. So over like the next 30 years or so. And shaded is where those changes are not statistically significant. And then the bottom is taking that exact scenario and offsetting the warming with stratospheric aerosols. And basically, it works remarkably well on temperature. So this is basically comparing points. The top row is essentially comparing point 1 and 3, and the bottom row is comparing points 2 and 3. Works pretty well on temperature. Actually works pretty well on precipitation in most places. There are some changes over land, and then there are some details, or so lots of changes over the ocean, and there are places over land where you see some changes in precipitation. Those are, I'd say, still a bit of a subject of research. They depend on the climate model. They depend on exactly how you're doing it, like what latitudes you put aerosols in. But by and large, this is the sort of result that comes out of climate modeling. So more or less, if you believe climate modeling, you would say, any impacts of climate change that are predominantly driven by temperature are likely to get greatly reduced if you were to deploy something. Impacts of climate change that are associated with precipitation are less obvious what the net effect would be of deploying. Okay, so I'm going to really quickly go through, this is sort of just some recent work of ours. This one was from a couple of years ago, just pointing out that if you inject at high latitudes, you can cool the Arctic quite effectively. We had a couple of papers last year looking more at the scenario space. So what happens if you wait to deploy? Do you get to the same state? Short answer is the climate model, at least. I don't know about the real world, but the climate model does not actually show any strong irreversibilities. And also looking more carefully at termination and interruptions and so forth. And then a fair amount of work looking at the latitude of injection. So this is sort of unpacking the questions. Quite often you'll get, if you deploy geoengineering, it'll do X. If you deploy stratospheric aerosols, it'll do X. It's like, well, Actually, it depends a lot on how you do it. And so, we have a paper that looked at the risks on the Antarctic. I'll mention that briefly. A paper looking at that we just submitted 2 days ago, looking at AMOC, Atlantic Meridional Overturning Circulation. Papers looking at ozone response. So just a few teasers on all of those. The maps on this one show Arctic sea ice, September minimum. Climate models may be under predicting how rapidly we lose the sea ice, but even the climate models basically predict that we lose September sea ice. If you do geoengineering, you restore it. You can restore as much as you want, depending on how much you do. This one is the Antarctic one. The story on Antarctic is a little bit more complicated because the melting of there's all the ice sitting on land that is being held back by ice sheets in the water. Those are being melted from below. And in part, some of that is upwelling water from the depths. So there's a little bit more complicated story trying to understand how stratospheric aerosol injection affects that. This plot here is showing global mean temperature on the horizontal axis and the ocean shelf temperature over the West Antarctic ice sheet on the y-axis. And the line in the middle is basically just showing increasing climate change. So as I increase climate change, I basically follow this trend. Climate gets warmer, and the West Antarctic ice sheet gets warmer and presumably gets a higher risk of melting. To the extent that geoengineering takes you right back down that line, you would say it can compensate for the risks. And the answer is it's a little bit above the line. Not too surprising because of some inertia in the system, but how far above the line it is depends on how you do it. So there's some more research that needs to be done, but the short answer is if you are worried about sea level rise from Antarctic, then yes, this technology is something that could handle that. Again, this is the Atlantic Meridional Overturning Circulation, same sort of story. There were a couple of papers that came out last year. I think there's some, I would take those papers with a bit of a grain of salt, pointing to potential collapse of AMOC. My answer is, there's some people who say, oh, the science is uncertain, therefore we should assume that there will be no collapse. I would say that's no different from people saying the science is uncertain, therefore we should assume climate change doesn't exist. Reality is there is a risk, there is some probability that AMOC will collapse. We do not know what that probability is, nobody does. If you were to do stratospheric aerosols in the northern hemisphere, at least in the climate model, that does in fact, in this case, it didn't just maintain the strength of AMOC, it actually restored AMOC back to earlier time. In contrast, if you do stratospheric aerosols in the southern hemisphere, it doesn't really do anything. So that was just submitted 2 days ago. Ozone, this is one of those things that's been around for 20 years. Everybody has said, oh, you can't do stratospheric aerosol injection because of ozone loss. So just to show you what the plots look like, the Antarctic one is on the far left. This is the, and basically the black line here is showing you climate change. The Antarctic ozone is recovering under climate change. If you were to start the blue line here in 2035, you started deploying geoengineering in 2035, by 2040, you would have brought Antarctic ozone all the way back to 2025 levels. If you look at the rest of the planet, in the Arctic, if you deploy stratospheric aerosols, you actually enhance ozone in the Arctic. And in the mid-latitudes, the signal from stratospheric aerosols, the oscillation here is from the solar cycle, the 11-year solar cycle. And in the mid latitudes, basically the response to ozone is less than the response to stratospheric aerosols. So I look at a plot like this and I go, why are we still talking about ozone? It is a non-issue. Okay, so here's my summary of what we know. In principle, it's easy to do. I'll spend a few minutes talking about that. We know it would cool. We know that anything impacts that are driven by temperature would get better. But we also know it does not affect the climate in the same way as greenhouse gases, particularly when you look at precipitation. So if you asked, what is the probability of extreme rainfall in Pakistan causing floods or a drought in Central Africa, those questions need more careful attention. I basically said that. It does do other things. It affects ozone, that's a small effect. It does come down as acid rain eventually, that's a small effect. It does change the ratio of direct to diffuse light. It doesn't just reflect sunlight back to space. Sulfate aerosols actually scatter quite a bit. That has some unknown effects on ecosystems. On the whole, that would actually virtually certainly increase photosynthesis, land photosynthesis. But the overall ecosystem responses to things like that, I would say, are unclear. I see Jessica's on here, so and if you spend 100 years increasing diffuse light, now the understory of forests gets better light than it used to, and it could potentially have long-term effects on ecosystem competition. Whether that's significant compared to climate change, it seems speculative. And then on the societal side, I basically already said all of that. Yep, there's issues. And I wrote this slide a few years ago, but I think it's still largely true. There's actually a fair amount of impact work going on in the developing world now. But I'd still say by and large, it's mostly developed world. Most of it is still probably more Earth system running climate models and so forth, rather than saying, let's understand how direct diffuse light changes affect ecosystems or something like that. And I still would say a lot of it is somebody is interested in a particular thing and goes and looks at it rather than anything systematic. So what do we need to know? And I would actually start that by saying, well, what's the question? And so I tried to write a question. What do we need to know if you wanted to decide, there's a big question, like who's deciding, right? If there was a decision to be made about whether to start, that decision is in some sense, do we start ramping up cooling to some level? And then you have to pick some level so that you can start making quantitative comparisons on the risk assessment. So I picked a 0.5 degree. What do we think would happen? How confident are we? What are the risks? How would you actually go about deploying? Like, how do you actually do this? I'd say not much point in telling people how to deploy, what the effects would be if you don't give them the option to actually do something with that information. And the answer to that question affects everything else. So if you look at what's in an IPCC assessment report, it's primarily would be those first two questions. To me, this third question about thinking about what deployment looks like more seriously has essentially not been funded. So let me say just really, really quickly, most of the simulations assume some global deployment where you put stuff in at lower latitudes. To do that, you have to get up to 18 to 20 kilometers at least. We don't have airplanes that can do that. I don't think it's hard. And I can say that because I've got an aerospace engineering background. Right? Somebody's done a paper study and said, here's how you would design an airplane to do it. It'd be at least 5 billion in 5 years to develop, but we're pretty sure it could be done. But you could start at higher latitudes where you only need to get up to something like 13 to 15 kilometers. I'm not 100% certain right now how bad it would be if you went as low as 13 kilometers. But if you could do it at 13 kilometers, you could do it with 777s. And the reason for mentioning a 777 is that's still a production aircraft. That gets you a 100-ton payload, um, basically not a problem at all to build up a fleet of aircraft that could do this. You do need to design the tank and nozzles and get the airplane recertified and build all the ground infrastructure up and so forth. So even there, I would say, that's why I say if you give me a check if you gave somebody a check today, that's still at least a 5-year effort. And then the one other thing I would say is, you don't start by just deploying. The very first thing you would do is fly one airplane up. You release a bunch of aerosols, a bunch of sulfur dioxide. You validate your assumptions about size, distribution, and so forth. Personally, I think we should go design and do that experiment. That has no effect on the climate. If what you see is inconsistent with our climate models, well, you go back and you look at the modeling again. You figure, all right, let's go back to the drawing board and see what went wrong. If it does, then maybe the next step is you go do this for a season. You're still, if you're doing it with one or two airplanes, you're not really affecting the climate. But now you can basically check the aerosol distribution in the stratosphere. There's really no physical risk even to that experiment. It's still tiny. That basically, again, lets you validate all of your stratospheric assumptions. And only if that looks good, then you might consider ramping up the amount of cooling. So that's sort of what that process would look like. I might wrap up here and take questions. The one additional thing I will say is I'm on the scientific advisory board. Okay, I'm the chair of the scientific advisory board for a new nonprofit called Reflective. You should check out. I don't think I have the link handy, but you should check out their there's a emulator put together that's really slick for communication. So you should check that out, and we will publish soon some of what we discussed on the scientific advisory board about the key risks. Herb, can you hold your question for just a second? And I will pause. I don't even think I need to read this last question because I said it all. So I'm sure there's lots of things I didn't say, but I'll open it up for questions at that point.
Thank you so much. This is a wonderful, brilliant talk. With that note, I open the floor for question, and Herb is the first one.
Thanks, Doug. I always learn so much. Even when I hear you say the same thing, I learn so much the second time I hear it.
I was going to say, you've heard me before, and half the slides are the same.
Exactly. So if I could, two questions that are somewhat related. First, the issue of moral hazard drives me. I don't know if it drives me as crazy as it does you, but certainly I find very disturbing. And I had the opportunity. I was in Baku for COP29 to talk directly to Al Gore, and I, asked him. I knew he was against. He's always publicly stated his opposition to SRM, and I started my conversation by acknowledging that, and asked him if he would reconsider that. And he gave me this scowl that looked like, who the hell brought this guy in here? And he basically just simply said, moral hazard, oil companies. So no, it was dismaying that was the argument he used. So I guess my first question is, what do you think is behind that? Does he really, does he and the Michael Manns and all these other folks who proclaim this moral hazard, do they really believe that? Or is it just a kind of smokescreen for other concerns or fears? And the second question is, I was reading your paper, I think it was 2019 or thereabouts, where you talked about mission-driven research versus what you called, and I didn't know that was a term that's used, curiosity-based research. And when I was at the COP, I talked to some climate scientists trying to urge them to advocate for mission-driven research. Have we made any progress in the last 5 years towards moving towards mission-driven research? It seems to me that's absolutely critical. And I think you've been involved in a couple efforts in that area.
Um, so I mean, see what order to take that. I'll answer the second one first because I think that's easier. I would say that is fundamentally the reason that we set up reflective.
Okay.
Um, and if you, I didn't spend any time on the slide, but uh, we are trying to do much more sort of hard-nosed, what's the actual, if we want to actually inform a decision, what's the roadmap to get there? What are the priorities? What are not the priorities? I do think there's lots of things that need to be answered, but I have certainly seen people say, so I have heard somebody say, oh, in this climate model, the ozone went up by 2 Dobson units. And in this climate model, the ozone went down by 2 Dobson units. We don't even know the sign. To which the correct answer is the 11-year solar cycle has a way bigger effect on tropical ozone than 2 Dobson units. And if the answer is so small, that's not a priority. So I think there's still to the extent that it's driven by scientists looking for funding, there is often a little bit of this is my pet piece. But I do think there's now, if you look back 10 or 20 years, I think a lot of us might have been, oh, this is sort of curious, this is interesting, let's try to poke at it and see if we understand it. And now I think there's a much broader, wait, the reason we're doing this research is because we might need to deploy. Hold on a second, how would we actually go about deploying? And so that's where I start doing, walking through these pictures of saying, okay, well, what's the first test that you would do? What would you learn through that test? How do we conduct that test, and so forth? On the first question about the moral hazard, my sense from talking to some people is that they really do truly believe that. And they are very, very invested in their belief. I don't want to belittle it completely. I think absolutely that there are forces in the US, for example, that will latch onto this and say, great, there's a solution. We don't need to cut our emissions. The reason I wouldn't worry about that myself is they're starting from the premise that they're not going to cut emissions and regulate fossil fuels. They're just going to grab whatever, you tell them that you have to say climate change doesn't exist. They're like, okay, I'll say climate change doesn't exist. Right? It's not actually a cause and effect. Plus the fact that I find it a morally repulsive viewpoint.
Yes.
But yes, I do actually think that from talking to some people, I think they really, really, truly, they've never really even questioned the assumption. They're absolutely convinced that the only reason anybody talks about this is an excuse not to cut emissions.
Okay, thanks.
Thank you, Herb. Our next person is Mike McCracken. Mike.
Thanks. So Doug, that was interesting. I have just 2 quick comments and a question. So on CDR, on the moral hazard argument, I did hear somebody, and it seems reasonable to me that the moral hazard argument applies more to CDR than it does to SAI.
Yep, something. No question. Absolutely no
and
question.
And then on the termination shock issue, we'll only have a termination shock issue if mitigation and CDR don't work. Okay. So the people who are proposing that as a major issue are saying other approaches won't work, essentially. It seems to me. So those are just
so basically the termination more or less is if you were, halfway well into a deployment here, and you were cooling the planet by a degree, say, and then you suddenly turned it off, over the next 10 or 20 years, it goes back to where it would have been. And then the presumption is that because that is rapid change, that's potentially worse than if you had never started.
Right, but some people say
that's arguably a fair. I think the answer is we don't even know.
Well, we've had an argument where people say, oh, it's going to go back to 3 degrees or something like that. Well, if it's going to go to 3 degrees, that means mitigation and CDR haven't worked.
So
and
where the termination shock argument makes sense is for the people who have a really strong belief in the moral hazard. Then their view is that you're not actually going back to where you're going back to something that's worse because somebody said, oh, great, now we have this. We don't need to cut emissions as much. We don't need to invest in CDR as much. It's less pressing. And so you're getting back to a worse state. But the other thing is, right, is one of the reasons that we wrote that paper, that Jared wrote the paper last year on, or this year, I guess, on interruptions and stuff is, if you restart it within a year or two, it's not actually, it's not great. It's not that bad.
Yeah. So the other question is, why have you considered just an issue of putting aerosols over the Arctic in a couple of the summer months when it's low reflection?
Yeah, that's basically.
And not doing it, not even worrying about going up to the stratosphere. The atmosphere in the Arctic in the summer is sort of not too active and doesn't remove sulfate. So you might get sulfate lifetimes if you time it well with meteorology a week or two. Could you do that now and just try and keep the energy input to the ocean, try and cut that down? And would that affect the latitudinal pattern and everything else, or just try and keep the Arctic ocean cool, or maybe the Southern Ocean too, but do it with tropospheric aerosol?
Three things quickly I would say is, one is, yes, we were only injecting in the spring. There's no reason to inject all year round. We did these simulations with injecting at 15 kilometers. We are working right now to see whether 13 kilometer, how much of a penalty there is at 13 kilometers. But I would say in terms of how much you need to do and deposition and so forth, the higher you go, the more efficient it is. And so given that it would be easy to do at 13 kilometers above the tropopause, I don't see why you would do it lower.
Well, because I could do it easily now, even though it takes more work, and I don't have to worry about 5 years of development for aircraft.
It doesn't take any more effort to do it at 13 kilometers than 10. You're still using, right? Commercial aircraft, Boeing aircraft can get up to 13 kilometers, 13.1. The reason I say it takes 5 years is you still need to design the tanks that go in the airplane and the spray nozzles, and you need to test all that stuff out, and you need to recertify the airplane, and you need to build the ground infrastructure out. These things take time. Maybe it's 3 years, but it's not next year.
Okay.
All right.
Maybe I can do it from land and mountains in the surrounding area and let the air flow in, but yeah, okay.
Okay, thank you, Mike. The next question goes to Gregory Sclater. Gregory.
Hello. Thank you for your presentation, Dr. MacMartin. Appreciate it. You had there's many questions I would have, like everyone else, but even though I've heard most of this before, but in one of your slides, you showed several of the problems that you felt were significant to deal with before deployment. And yeah, it was different, but that's fine. And you mentioned, a botched deployment is a problem, but the one that you were focused on or identified as perhaps the most critical one was conflict as a result of, because it's a global thing and if you don't have agreement. So the thing is that the argument, the danger, the moral hazard of conflict or whatever, is there's an assumption there that if you delay SAI, if you keep delaying SAI, that somehow people will come on board and that there will be a more cooperative approach to SAI deployment. And I think the opposite is probably true, because as things get more chaotic under the stresses of climate change and global warming, I think the possibilities of cooperation are are decrease rather than increase, and I think that argument that should be pointed out. Also, the very appeal or the very appeal to the danger of conflict is itself a moral hazard argument that is dubious in the sense that it sort of means that we have to wait until things get so bad that nations agree to cooperate, that the large nations agree to cooperate amongst each other to deploy, and therefore avoid the conflict.
That's
But
not
that,
what I disagree.
okay.
So what I would say, if you were to deploy today, I actually do think that there would be some serious issues. But how do you reduce those risks of conflict? One answer is you make sure there's a nice, robust bit of scientific knowledge that everybody agrees to, and a well-written, IPCC chapter that says, look, here's what would happen, and a good plan that says, okay, here is how we're actually going to go do it, right? We're going to go do this experiment. We're going to go measure these things. We're going to compare it if we see something different. Right now, you get like, right now you've got stuff like that, the UNEA meeting last year where African delegations were more or less informed by ETC, had no idea what they were talking about, and didn't even want to hear it mentioned. And I do think the situation has changed a huge amount, even in the last few years. 5 years ago, certainly 10 years ago, people didn't even really want to talk to me sometimes because I worked on the subject. Now, almost everybody, there's a vocal minority that's opposed, but they're a tiny, tiny minority. Almost everybody is strongly supportive of research.
Okay,
It's
let's
a
go.
big shift. And I actually think if you want to have a responsible deployment, you pretty much got to go through like, here's a good, robust body of knowledge. You have to actually answer everybody's questions. And it's one thing for me to look at all the simulation output that I've seen and say, I have a pretty good sense from looking at the papers of like, oh, I can disregard this paper because I know why they got the weird result they did, and I can disregard this, and I can sort of get this general sense of risks. But we got to be able to communicate that. And that takes more than just
Yeah, I get
saying
that.
I've got a general sense that I think this is less risky, right? You got to be able to
So,
need a more robust way of convincing people than that.
so reflective is designed to do that job, I think, among other things. And you put a time scale in your of 5 years. Do you think in 5 years we will have accomplished this case, the case for SAI adequate?
I don't think that's ever something that's done, but I think in 5 years we will be in a much better position. It's not just reflective, right? There is now more.
Oh, I agree. Yeah.
In WCRP has a lighthouse activity. I have a colleague who was at the IPCC scoping meeting last week in Kuala Lumpur. I'm not allowed to tell you what the outcome of that was, but I think it is likely that there will be better coverage in the next IPCC report. SRM 360 has also just been formed. There is sort of more momentum, and I think a much stronger push to being able to write good, robust assessment reports that are complete.
Okay.
And people like Jessica can help us on the answering the questions about ecosystems.
Thank you.
Thank you, Gregory. In the interest of time, just want to make sure that, if you want to extend 15 minutes or half an hour,
I'm fine.
Douglas okay? Doug, are you okay with that?
Yeah, I'm fine with that.
Okay. Our next question goes to Jessica.
Well, hello, everyone. And I agree with you that every time I listen to you, Doug, I learn new things. So yeah, me too. So I have a few comments and suggestions. I think one of the things we definitely need to understand impacts on ecological systems and on people is more work on downscaling, because as an ecologist, I think it's not going to be, it's bad, it's good. No, it's going to be bad in some places. Some kinds of things are going to be at risk. Other things will be ameliorated, and we need to have that kind of information. So that was one comment.
Yep.
Another
100%.
comment is all of this discussion just raises even more the need to have more social scientists deeply involved in this research, because so many of these questions are within the realm of social science. Also ecologists, but we need to have more social scientists talking about this relative risk, which is, I think, critical, relative costs, relative benefits, who has the burden of the costs. How do you get people discussing this in a way that is not like that unfortunate interaction with Al Gore, which I'm almost laughing about. So it's like, well, people aren't listening to Al Gore anyway, which is like, I think he's a hero. Anyhow, some of the relative risks are migration. So immigration, huge numbers of people. It's not just warfare due to the implementation of SRM. You can have gigantic mass movements of people where you can no longer survive outdoors, you can no longer grow crops, and so on. And all of these people who are so worried in this country about immigration, well, just wait till you have hundreds of millions of people who can't survive in the places that they're living now. And there's nothing that you're going to use to stop hundreds of millions of people. So those are, we need more social scientists. So the other thing I wanted to bring up were one of the things that I just started thinking this is a real issue. If you were going to use SO2 as your aerosol for injection, you've got a lot of handling of SO2 on the ground. And that seems like a potential, everybody is going to be really careful all the time because we've never had any industrial accidents, right? No, they're not going to be careful, and they're going to have spills, and there's going to be burns, and there's going to be how do you ramp up the manufacture to the level that we need? So, oh yeah, no, I see John had a comment. No, I agree. Yeah. I'm agreeing about the immigration, that this
People
is
ask
one
me
of the
what's
arguments
the
for
number
it.
one effect of climate change on the US? My answer would be immigration.
Yeah. Well, and flooding and, all those kind of things.
If
Fires,
AMOC shuts
fires
down,
have been
that's
pretty
it.
substantial, and so anyway, yeah, I'd like to have people thinking a little bit more about how are you going to manufacture all that SO2 that is needed continually, and how do you do that in a way that is more safe rather than less safe and not chaotic.
This is, I'd say, when we as the scientific advisory board for Reflective actually started really going, what do we think the big questions are? We wound up putting a fair amount of emphasis on some of that, like, okay, it's one thing to just go take a climate model and put SO2 in there, but like, how do you actually go? And it's another, we could go say, all right, well, this airplane can get to this altitude or so forth. But all of this infrastructure to do that needs work.
Yeah, it sure does. So one
And
other
someday,
one other
sometime
quick
an
comment.
airplane full of SO2 is going to crash.
Yeah.
Then what?
Yeah. Or just manufacturing it and shipping it to the places that the planes are taking off from. All of those that's a relative risk as well.
Yeah, it's a risk. I don't think but yeah,
It's a risk. It's just a risk to, so the other thing
Wake
is
did some nice analysis, but he was assuming you were operating out of a commercial aircraft. And I'm like, oh God, no.
the other comment about moral hazard. I think that response of a lot of people is due to the way this was first introduced to the public, which was by those high-tech bros. They were the ones who were first promoting this, and they were saying we can use it instead of emission reduction. And then that got sort of fixated in people's brains. And all the climate scientists that I've met, and I have had the privilege of meeting a lot of them now, including you, Doug, have said, no, you have to start by reducing and eliminating the emission of CO2 from fossil fuels. And so we all think, yeah, of course you have to do that. But that's what I think it is. I think they're harking back to those tech bros who are saying, yeah, we could do this and not reduce CO2 and CO2 emissions. And my answer to that is, well, how well is, okay, so we don't have that moral hazard of SRM right now. How well is that working for you? Like, so we are doing a little this and a little that. We have the highest level of emissions and highest level of CO2 in the air that we've ever had and the highest level of warming. So the fact that we haven't used SRM, it's not like we already have a moral hazard. And the biggest moral hazard is air conditioning. So people can go, who have the resources, can go into their nice air conditioned homes and offices and cars and say, well, we don't really need SRM, we're fine. So I think air conditioning we should ban all air conditioning and not have a moral hazard from that. So those are my comments.
So I will go to the next Dennis, Susan, John, and Doug. So the four, and then I will close. So let us say we still have a few more minutes. I mean, I'll go up to 11:30 if everybody is okay with that, and we should make a hard stop at that time. Dennis, your question.
Sorry. Yes, I was on mute. Great to participate here, Doug. And I have two quick things. One is that in a prior presentation, you talked a lot about the need for a very credible risk analysis at a global scale. Very very high level type thing, which would be organized at this point in time. But have you seen any progress in that direction? And maybe more relevant, have you been thinking about doing a comprehensive risk analysis with your own colleagues, workshopping type of thing, which I think would have also a very, very effective and would be a very great contribution to the whole subject.
I agree. It's an area we're working on. Right. So broadly, I think there's two pieces, right? One is the comparative risk assessment, but then even with a particular thing, rather than just saying, oh, we don't know X, is trying to actually be more quantitative about how wrong can we be and what are the consequences of being wrong. As to say which uncertainties actually matter and need to be resolved, and which uncertainties are just kind of like, yeah, it's a thing, it's okay. We make decisions under uncertainty all the time. I think the answer is a lot of these things, it's a big research effort. It's not just go organize a meeting and sit down and say, we've decided that these things are lower risk than that. Having said that, we did try. And this plot here was actually the output of some of that, of the risk register side of saying, how big is an uncertainty versus how consequential. This is the opinion of 5 of us sitting down in a room for a week, for 2 days, trying to say, well, what do we think are the biggest risks? And arguing over, well, how big of an effect really would that be? So there's progress in that, but it's not where it needs to be.
Yeah, very good.
Okay, next question to Susan, then John.
Hi, yeah, thanks. Very interesting talk. I was wondering, at the beginning, you mentioned that once we start deploying, we'd see some of the effects and then we could adapt or revise our strategy. So
Yeah,
I was
we could unpack that one for a long time.
Yeah, I'm not an expert on the attribution at all, but I was just wondering whether it would be possible to separate out the effects of SAI from, let's say, variability, natural variability. Would we be able to say, let's say 3 years after, okay, we need to revise our strategy because, I don't know, we caused changes in precipitation that we didn't want to, and that was because of SAI and not because of increased greenhouse gases or whatever. Like, is that possible? Is that really going to be feasible?
So I'd say the answer to that question is probably an hour conversation and then a few years worth of research.
Okay.
So there's something, basically the stratospheric stuff, the signal to noise would be huge quickly. So, if we are wrong about anything in the stratosphere, we will learn that before we even have a climate effect, basically. The surface stuff, like, oh, did we shift ITCZ in some unexpected way? Yes, you're right. That basically has to then go to, standard attribution methods and compare, there's what do you expect to see? What did you actually see? How do we tell whether the difference is natural variability and so forth? Broadly, I would say, yes, that's a very, very serious issue. But it's not, I guess what I'd say is it's not like jumping out of an airplane and hoping your parachute works, right? And one might reasonably assume that if you honestly cannot tell, maybe it's not that big a deal at that level of cooling. And so I think that what one needs to do and why there's a research question is sort of say, well, what's the scale at which a certain impact would become a problem? What's the scale at which you might learn that it's going to be a problem? And which of those happens first?
Yeah, okay. And if it is a huge problem, then probably it is robustly attributable versus if it's just a small change.
Right,
Okay.
right.
If I may, I also have another question that relates more towards separating, like in the risk framing, right? We have risk of climate change versus risk of SAI, but the risk of SAI is really kind of residual risk of climate change plus the risk of SAI, I guess. But it's more related to the more SAI gets included in also the policy discussions and the policy framing. Isn't it hard to then actually present these worlds in such a separate way? Because normalizing SAI, like we, for example, normalized CDR, and then CDR now is in every pathway, and it's kind of expected and normal that we will have to do that, or that we are going to do that. Isn't that kind of the way we're moving with SAI? And in that way, it's going to be very hard to single it out and present two worlds of like a world with SAI and a world without SAI. I'm not sure. It's not a really clear question. I guess I'm wondering, do you agree with the statement of SRM now is where CDR was like 10, 15 years ago? And do you see SRM being as implicated in every scenario as CDR is nowadays? Or do you think these are really two different concepts and they will be taken up by policy in different ways?
I think they are completely different concepts.
Okay.
I think the reason that CDR is a moral hazard is partly because of time frame and partly because of the fact that it's working on the same thing, right? It doesn't, some level, it doesn't make any difference whether you fail to emit a ton of CO2 or emit it and then suck it back in. And so in that sense, it's easy to say, oh, well, we're just going to emit more now, and our plan is to suck it back in later on. It's, from a climate perspective, other than the time delay issues, it's kind of comparable. Personally, my sense is if we get to a point where we're deploying something like this, nobody's going to look at that and say, that's the world we were hoping we would wind up in. And so I think about it a little bit more like along the lines of, if you have an airbag in your car, you don't say, woohoo, I can run the red light now. If you've got anti-lock brakes, well, maybe I'll drive a little faster because I'm more confident I can stop. But and on your earlier point, I agree that they are not fully separable, right? As soon as you start talking about more serious policy, more scenario-based analysis with SAI or SRM more generally, then yes, some of that moral hazard stuff might start happening. In fact, if you were deploying for 50 years, you don't have a counterfactual. I mean, you you never know what the world would have been like if you had not deployed. And so you would never, ever have any way of knowing whether there was a moral hazard or not, even after you deployed.
Yeah.
You might be able to find people's quotes and say, oh, we've decided not to do X because of geoengineering, or we decided to do it, or what have you. But you never know what they would have done otherwise.
Yeah. Okay. Okay. Well, thank you so much.
Thank
So
you.
basically, I'm agreeing with you. John and Doug.
John and Doug, right?
Yes, I agree with both of you.
John, are you okay? John, not Doug. You go ahead.
I'm not hearing from John. He usually has problems.
Yeah, no, I've just unmuted, but my wife is making a noise in the background. Can you stop, Alice? Okay, I've got kind of two sets of questions. One fairly straightforward, which is technical. Do we know enough about the circulation, the dynamics, and the immediate circulation in the stratosphere to be confident that the aerosol will move in the right direction and spread out and evenly and eventually leave?
Kind of. I mean, I think it's just a question of how accurately do you need to know that.
Okay,
we generally understand the Brewer-Dobson circulation in the stratosphere. Different climate laws,
okay,
different things,
so we really need some modelers to be able to model what's going on and the effect of
I mean, we
what you're
model
doing.
it, right? We model it. It looks kind of like the observations we have. Does that saying we know it well enough? And one has to be very careful about defining what well enough is. But I think my answer would be for the first decade of deployment, yes, we know it well enough.
Mm.
Right?
Because
You're not going to be cooling the planet by a degree at the end of a decade.
what I'm thinking of is when you actually deploying at the moment of deployment, the hot, cold and hot spots are going to be different around the planet, and you might want to inject at the time when there's a hot spot where you are, and rather than when there's a cold spot, because you might make things slightly worse.
I mean, the time scales of the planet responding are slow.
Yeah. Okay. And the other quick technical question is that you were relying on humidity in the stratosphere. Is that a problem?
We're relying on, I mean, if you're injecting SO2, you're assuming there's enough OH in the stratosphere to oxidize it into SO4. That is probably, I mean, overall, that's perfectly fine, right? Pinatubo can put 20 million tons of sulfate up there. There's enough water vapor for that, right? The stratosphere overall is dry, but there's certainly plenty to oxidize the sulfate.
Okay, that was really all my reassurance on the technical side. My main problem is that I think we need SAI desperately, urgently, to avoid tipping points in the Arctic. And we've got a tremendous amount of buildup of heat and heat flux flowing into the Arctic because we've lost so much albedo there. And there's also heat flux coming in from the Atlantic water flowing into the Arctic, and to a certain extent the Pacific water. There's a vicious cycle of warming and melting in the Arctic, which has to be broken, and SAI is the only thing that can possibly break that cycle. But if we got to a point when even that wasn't enough, the implications are that future generations would have to deal with meters of sea level rise from the inevitable meltdown of the Greenland ice sheet, and also a change in the climate distribution around the planet for two reasons. One is the reduction in the temperature gradient, which holds the climate systems in position, and the other is the AMOC going and changing the climate in a different kind of way. And we get a completely different climate configuration, atmospheric circulation configuration for the planet. These are such colossal risks that but they are not things that you can say, oh, this is happening, therefore we've got to stop it. It's a risk from something in the future becoming inevitable. How do you deal with that politically?
The short answer is I don't know. So I would say I'm probably, I'm at least somewhat in agreement with you. I don't think these things are, I don't know what the probability, what the future holds under climate change. Nobody really does. We're in uncharted waters. But I would say from a physical climate perspective, I would say there is absolutely no rational or any rational risk assessment would start deploying as soon as you possibly could. I think that is, my personal view. I think that's absolutely unequivocal. So the reason to not start as soon as possible is fundamentally comes down to the international politics of it. Is there's no point in just doing a little bit for a few years, right? They only get the benefit if you actually do a sustained deployment at scale. And so if you then say, well, how do I get to a sustained development at scale? My answer is starting tomorrow is probably not the best way to do that. But when
my problem is
yes, I'm kind of making a very strong statement that we should be deploying now if the only issues on the table are the physical climate. There's just no rational argument against that position.
There's an argument that you're going to need 5 years to ramp up anyway. So we should be starting by doing the development starting the development of the nozzles and the aircraft and things now.
Agree 100%.
Yeah. So I think it's really urgent to start the preparation so that we're in a position in 5 years to have full strength in 5 years. And by that time, we'll know whether it's anything terrible is going to happen as a result of what we hadn't anticipated.
We ought to be being really clear about what can you do with existing aircraft. What is it? Start thinking about how would you design retrofit kits for them. How would you measure where the aerosols are going to give people confidence? Those are, to me, like super, super urgent questions.
So but the political
politics, neither you or I know how to solve.
The political problem seems to be that nobody really worries about future disaster. They're only worried about
people don't.
Okay, sorry.
Anyway, yes, John. I think we're broadly.
We all agree. Just just in the interest, I'm sorry to interrupt you, John and Doug. I wanted to give Doug a chance to ask his question because we will make a hard stop at 11:30 my time, so 9 minutes.
Doug, nice to meet you. The other Doug.
Yeah.
So in the interest of time,
get confused on an email, like, wait, who, what?
Yeah, I know. I see my name at the top, and I think, oh my God, I got to answer this email. It's to you. So in the interest of time, I'm going to speak very quickly backwards, and I'm going to throw you some softball questions, and maybe you can answer them yes or no. So I like to think in terms of who is the audience and what is the message, and I think in terms of a pyramid with the benevolent dictator at the top and the rest of the public at the bottom, at the base of the pyramid. we got to find the right audience to talk to get action happening. So my question is, very briefly, do you have contact with people like Bill McKibben and Michael Mann and Catherine Hayhoe and people like that who are very influential and obviously thinking the wrong thing about SAI? And is there any way that you as a scientist could lean on those scientists? Bill McKibben is more of a social scientist, but I have a campaign with him. But do you have any contact or any influence with any people like that, the right audience to perhaps move some other people?
Nobody's going to change Mike's mind, Michael Mann. So some of these people, I'm not going to try to move them. I would just, eventually they'll be in the minority. But no, I don't have the right contacts.
Okay, that's fair. Thank you.
So let me ask you a question. So it looks like there is a lot of, deployment question, I understand there is a lot of resistance. What is the resistance? Why is there such resistance on doing the research, doing the designing the test plans? Why is there that, R&D effort? Because this is something understandably would be needed, and there is some level of understanding that risk is there. So to mitigate that risk, we need to be prepared. So what is it?
I think the opposition is less than some people think. It's not zero, but I think it's a small, very vocal minority, and a large uninformed group that have been told stuff by that small vocal minority. By and large, like we go around Cornell and basically all the way up to the top of Cornell to the president, everybody's like, great, how can we support your research? We're delighted to have you here. That is the message that I get virtually everywhere. I, of course, I'm white, I live in a developed country, but I've given talks in the developing world, and that's by and large the reaction I get in the developing world as well, is like, look, climate change is a problem. If there is something that can help it, we want to know about it. So I think as it has become more and more and more clear that emission reduction is not going to happen in time, I think that attitudes are changing. I think what's unclear, there's a tendency among some to draw a line in the sand on outdoor experiments. And my view is that is sort of a deliberate tactic of saying, it's pretty hard to argue about Doug going and running a climate model, but hey, we can go argue about this. So I'm perfectly fair game to say, what's the next, what do I want to focus a pile of research on over the next few years, is trying to figure out, okay, let's go design an experiment that would actually be useful and answer relevant questions. I have a little bit of a beef for those who are familiar with ScopeX. My sense was that the way that was talked about was, hey, we're scientists, we want to do this experiment, it's small, you should let us do what we want. Rather than saying, look, this is a really important subject, there is such and such an uncertainty, the only way to resolve that uncertainty is with an experiment, this is the experiment that will do it. And here are the risks of that experiment, and we believe them to be very small, right? So, there's sort of a level of maturity in how one treats one's audience. So we'll see what happens, but I think we need to go be serious about saying, what's the next thing? I mean, there's piles of modeling research that need to be done, but we also need to go figure out how would we start resolving any of these uncertainties in the stratosphere. That means we need to take a plane up there and start releasing stuff and measuring it. So let's go figure out how to do that.
So we are going for next 5 year, starting from January, intense campaign in India, starting with India. So we'll targeting about 2,000 participants in each year, and then have a conference, annual conference on specifically on solar radiation management to influence policymakers, the media, and the scientists, all of them together to have a national conversation on this thing. That is the target. So this is very helpful for me, and maybe at some point, if the time is appropriate, we'll include you if something progresses on this part, because
Sure.
that is the idea of funding and doing the R&D to get ready for answering such questions, to get ready for deployment. These questions are still open, there are risks, and that needs to be answered.
Yeah, I think, you know, by and large, I think most people are uncomfortable with deployment today, and that's okay. But I think by and large, most people are comfortable with research.
That's what we need to start there. So wish me good luck.
So yes, let me know how it goes.
Thank you so much. This is such a
Thank you.
wonderful talk, the audience participation that really makes.
Yeah, that's the fun part.
Thank
Sorry,
you.
I know half of you have seen a bunch of my slides before, so I tried to add a few new things in.
Okay, have a nice day.
All right, thank you. Bye.
Thanks, Doug.
Thank you.
Merry Christmas.
Merry Christmas.